Okay, so good evening everyone and welcome to the 12th session of this course Measure and Integration. So today I think there are very few things to say. So mostly in this session we'll be solving problems related to the LP spaces and a bit of uh, convolution maybe okay, related to some convergence thing, that's all. So I'll start with some of the theories that you have seen in this week. So let us start with this fact that completion of CC functions, that is continuous function with compact support, is dense in LP space, right? So we know that this CC omega, so where omega is some open subset of Rn, okay? So it's some open non-empty, so non-empty open subset of Rn. So we have seen that this Cc omega is dense in LP for P less greater than equal to 1 and less than infinity. And I have stated earlier, and in fact we have shown, no, we haven't shown that this is not true for P equal to infinity. And this is what we'll show today. Okay, so I mentioned in the last session that this Cc infinity, okay, I mean you can remove this infinity also, but it's true for infinity as well. Okay, so this Cc function with respect to this L infinity norm, if you take the closure, so that will give you C0 space. Okay, so I'll show today that this Cc function, the closure of this Cc function with respect to L infinity norm is C0 omega. And what is C0 omega? So this is the space of function which vanishes at infinity. Okay, so space of continuous function vanishing as, or let me write it in this way, space of continuous function such that mod of fx goes to 0 as mod of x. So this mod is nothing but the norm, okay? So Euclidean norm, as Euclidean norm goes to infinity. Okay, so this, we saw that this Cc omega, if we take closure with respect to the P norm, what we get is LP space, right? So this is when P is from 1 to infinity but not infinity. And what I am saying, that if you take this Cc omega closure with respect to infinity norm, what you get is C0 omega. Okay, and I stated this, but let's see the proof of this particular fact. Okay, so I'll prove this one. Okay, so before going to the proof, let us see one lemma which is coming from the topology. Okay, so this lemma is called Urysohn's lemma, and this is one variant of this Urysohn's lemma. Okay, and what it says, that if you have a compact set K which is contained in an open set U, and obviously both are subset of this omega, then there exists a function f which is Cc omega. Here also you can put Cc infinity. So the function f in Cc omega such that this function is bounded and non-negative. Okay, and in fact it is less than equal to 1, and on this compact set it is equal to 1, and the support is contained in U. So let me draw a picture to clarify this. So suppose that this is your compact set K, okay, and suppose this is your one open set you have is U. Okay, so this is your open set, maybe. Okay, so let me write that this is open and this is compact. Okay, both are subset of omega, so omega, maybe you can consider this bigger one as omega. Okay, so what this this lemma is saying, that there will exist a function which is Cc function, that is, it is continuous and it is compactly supported, such that the function in K, so in this region, f is equal to 1. Okay, so f is identically 1 on this compact set, and the support is a subset of U. So that means, so there will exist something which is lying between K and U. Okay, so maybe, so this I am saying that this is support of f. Okay, so I mean the whole region. So let me highlight it with some color. So this whole region, is the support of this f. Oh sorry, this region. Okay, so this is the support of f and it is contained in u. Okay, obviously it cannot be equal to u because support is compact. I mean this is what we are claiming. So it need to be closed, the first thing. So it cannot be equal to u, and it is obviously, it should be outside k, right? Because on k it is taking the constant value 1. So for the function to be continuous, it cannot directly drop to 0, right? So for continuous, it need to be, the support has to be a proper subset of, so it has to be containing k and not equal to k, and it is contained in u. Okay, so there will exist a function which is identically 1 on this inner circle, right? And it is 0 outside this region. So in this region, okay, I mean outside u, I mean outside this support, the function is 0, right? So f is 0 outside this. Okay, so it will take value 1 in this compact set, and the support will be contained in u containing k. Okay, so such function exists. So this Urishon's lemma give existence of such function. So if you have a compact set which is contained in some open set, then you have a function. This is what this lemma is saying, that there exists a function f satisfying this property, what I just stated. Okay, so we'll be using this Urishon's lemma to prove this this fact. Okay, to prove this one. Okay, so is this Urishon's lemma clear to you? Yeah?
Yes, sir.
Okay, so now we'll see the proof that this CC omega function, okay, with respect to infinity norm. Okay, so first thing is that, so this I'll give you an exercise. So the exercise is that CC omega with respect to this infinity norm is not complete. Okay, so this you just try to prove this, that there will exist a Cauchy sequence which will not converge in this CC function. So the limit will not be in this CC. Okay, so this I just leave in the as an exercise. So my goal is that, okay, this is not complete, so what will be the completion of this space, okay, with respect to this norm. So generally you know that the continuous function, we give this soup norm. Okay, so this infinity norm is nothing but the soup norm because we are dealing with continuous functions. Okay, so this is soup norm. So you know that this fact, you know, right, that if fn minus f converges to 0, that means in soup norm, that is fn converges to f uniformly, then you know that the limit function f is continuous. Okay, so this space c omega with respect to soup norm is complete. This is complete, but the CC space is not complete. Okay, that means the limit function will not belong to this CC space. The limit function will be continuous, but I mean you have to find an example for, I mean, so that such you can prove that, okay, this is not complete. So you have to construct a Cauchy sequence which converges to some function f, okay, or either it which does not converge to any function in this space CC omega. Okay, so that you have to check. Okay, so that I am leaving it to you. So what I will prove is that if you complete this space, okay, that is if you take the closure of this space with respect to this infinity norm, you get C0. Okay, so that's all I will prove. So let us begin the proof. The proof is not too hard. Okay, so you just take some, let f belong to C0 omega. Okay, I'll show, okay, that there exists a function g in, so what I will show, so we will see, we have to find our s, we try to find g in the space cc omega. Okay, so for given epsilon, for epsilon greater than 0, we try to find a function g in cc omega such that the distance between this g and f, okay, that is the norm and the infinity norm, is less than epsilon. That means whatever small distance you give, I'll able to find a function g which is in cc omega such that this g is epsilon far from this f, the given f. Okay, so this is what it means when we talk about closure, right? Closure by definition, this is what it means. Okay, so what we'll do, so you know that this f is given to be c0 omega, so I'll try to use some property of f. So c0 omega means outside a compact set this will be very small. Okay, that is another way of saying that it's c0. Okay, so since f belong to c0 omega, okay, so for epsilon greater than 0, so this is what I'll prove. Okay, so for epsilon greater than 0 there exists a compact set k in omega such that, okay, so for this epsilon, this k is depending on epsilon. Okay, so this compact set is depending on epsilon such that the function f of x is less than epsilon for all x such that mod of x is greater than k, sorry, for x not belonging to k complement. So that means, so what it says that there exists, so for given epsilon there exists a compact set k such that outside this the function is very small. Okay, that's all. This is what I have written. So this is the property of c0 function. Okay, so you get a compact set such that this thing happened. Now, so now we will use this compact set, okay, for applying Urysohn's lemma. Okay, so by Urysohn's lemma, there exists a function, okay, so let's denote it by phi in the cc omega, right, such that what are the properties? The properties where that phi is lying between 0 and 1, phi is identically 1 on the compact set. So I am applying on this k, on k, and support of phi is contained in that open set which is omega here, this. So support is contained in omega. Okay, so we have got a phi such that these properties hold. So now I'll define, so my goal is to find some g in cc omega. Okay, so using this phi I'll define a new function g. So define this g to be f of phi. Okay, now since this f is compactly supported, this phi is compactly supported, this f times phi is also compactly supported. Okay, so let me write some explanation. So phi compactly supported implies f phi is compactly supported. Okay, also you know that f and phi are continuous, right? So f phi continuous implies the product is also continuous. F phi is continuous. Okay, so this f phi belong to this cc omega. Okay, so we have got a function g such that this g is belonging to the space cc omega. Now my goal would be to prove that this g and the distance of g with f is very small, I mean less than epsilon. So let us try to prove that. Now norm of g minus f, infinity norm if you take, this is f phi minus f infinity norm. Now this is, so I'll take f common, then I'll have phi minus 1 infinity norm. Okay, so this is L infinity r or omega. Okay, now just tell me one thing, this phi is identically equal to 1 on this compact set K. Okay, so in that K, this is 0, right? So this is 0 on K. Okay, so instead of considering on the omega, we just need to consider on the K complement. Okay, so this is equal to f of phi minus 1 L infinity of K complement, right? Okay, now you know, so what is this? So let me rewrite the definition. So this is just the sup norm. So supremum x belonging to K complement of f of x phi x minus 1, right? Okay, now let us look at this quantity. So mod of fx phi x minus 1, this modulus of this less, so I can write this is mod of fx mod of phi x minus 1, right? Now you know that the phi x, the function phi, is lying between 0 and 1. Okay, so this is less than equal to 1 always, phi x minus 1, right? If phi x is 0, the at most value it can take is 1, this modulus. So I can write this is less than equal to f of x, and you know that on K complement this is less than epsilon, right? So oh, I think I'm writing on a wrong slide. Okay, just a second. Okay, so let me paste it here. Okay, now you know that this is less than equal to this, and this is less than epsilon. Okay, this is less than epsilon for x in K complement, right? So that is why this supremum over the K complement will always be less than epsilon, right? So we have proved that the distance between G and F is less than epsilon. So did you understand this proof, or do you have any doubt? Is this clear?
Yes, sir.
Okay, so now as I was saying that, okay, so what we have proved so far, that the closure of CC omega with respect to this L infinity norm is C0 space. Now my main claim was, okay, so this is what initially this is what I was saying here, that this is what you want to prove, but I'll prove a bit more. So as I have mentioned that this is not complete, but this space C0 space will be complete. So what I'll show, so this is what my theorem was, that the completion of CC omega is C0 omega. So this was step 1. Okay, so maybe if you want to consider, so this was step 1 where I proved. So let me write it here. So what I have proved here, so this maybe it would be claim 1, that CC omega, if I take closure with respect to infinity norm, is C0 omega. Now the next claim is that C0 omega is complete. So claim 2 is that C0 omega with respect to this infinity norm is complete. Okay, so I mean the proof is quite easy. So we'll start with the standard technique, that we'll take a Cauchy sequence and then we'll prove that it converges, and the limit is also in this space C0. Okay, so just start the proof. So consider, let Fn be any Cauchy sequence in C0 omega. Okay, so this means, so for epsilon greater than 0, there exists n belonging to the natural number such that norm of Fn minus Fm, so sup norm, which is infinity norm, is less than epsilon for all n comma n greater than equal to n. Okay, so now this is the soup norm, right? So this means that the sequence so okay, I think it was not required to write, but so this simply means that is Fn is uniformly Cauchy. Okay, okay, so now I'll use the result. I mean, this is one of the results that you prove in analysis course, that uniformly Cauchy implies uniformly convergent. Okay, so I'll just use that result. Okay, so this means that Fn is uniformly Cauchy. Okay, so this is, or if you want you can write it in this also, sorry, uniformly convergent. I mean, this is just by the fact that C omega with respect to the soup norm is complete. Okay, so either you can write this as your reason, this. Okay, so you know that it is a convergent. Now also that the uniform limit will also be a continuous function. So let f is equal to limit of fn. Okay, okay, so you already know that this limit is also continuous, again by real analysis course. Let f be this, then f is continuous, again the same reason. I mean, because C omega is complete. Okay, now what we want to prove, that this function belong to C0 space. Okay, so need to prove that mod of fx goes to 0 as mod of x goes to infinity. Okay, so this is what it means, that it is in C0 space. So C0 means continuous with this property. So continuity comes from this fact, from analysis. Now we'll prove that this goes to 0 as mod of x goes to infinity. Okay, so you had this estimate, right, somewhere. Okay, maybe. So since you can use the convergence definition, that since fn, so since fn is uniformly convergent or uniformly converges to f, therefore for epsilon greater than 0 there exists n in the natural number n such that norm of fn minus f, the infinity norm, is less than epsilon by 2. Okay, so this is what you have. Now this means that fnx, or what you can say, so this would imply that, so this is for all n greater than equal to n. Okay, so from here what you can say, that mod of fn, so I'm just taking at capital N, so mod of fnx minus f of x, which is less than equal to the infinity norm, okay, is less than epsilon by 2. So let us say this is 1. Now what you know, that this fn belong to C0 space, right? So this means, this implies that mod of fn of x, okay, is, so I mean there will exist a compact set, or so fn, so there exists, so given this epsilon, okay, so for this epsilon, so there exists a compact set k subset of omega such that mod fn of x is less than epsilon by 2 for all x belonging to this k complement. Okay, again I mean just the property of C0 function. Okay, so let me I think I should write here. Yeah, so let epsilon greater than 0 be arbitrary. Okay. Okay, so now you have this. So now we'll just combine these two. Okay, so now does mod of fx. Okay, I will just use the triangle inequality, but this is mod of fnx minus f of x plus mod of fnx. Okay, now you know that this is less than epsilon by 2 and this is less than epsilon by 2 when x is in k complement. Okay, so this is less than epsilon for all x in k complement, and this is what we wanted to prove, that this fx, the mod of fx goes to 0 as mod x goes to infinity. So this is nothing but epsilon formulation of that thing. So what I have written here, okay, so this is just epsilon formulation of that property. Okay, so what we have proven, that this fx is becomes very small after outside a compact set. Okay, so a mod of fx goes to 0 as mod of x goes to infinity. Okay, so what we have proved, that this limit what we are getting is not just continuous but it is vanishing at infinity. So this f belong to C0. Okay, so this proves that this C0 space is complete. Okay, do you have any doubt from this part, or was this clear to you?
Sir,
Yeah.
sir, we are using infinity norm as a soup norm.
No, we are not using it. It is. So I've said this many of the times, that for continuous function, the infinity norm is nothing but the soup norm. Right? For continuous function. So infinity norm you define, so for measurable function. But when it comes to continuous function, this infinity norm is nothing but the soup norm. You can prove the equality.
Sir, in the previous slide, there was C of omega with supremum is complete.
Yeah, this one. Yeah.
Yes, sir. Sir, where we use this in?
Oh, so I am saying that uniformly Cauchy implies convergent, right? So I mean, Cauchy is convergent is given by completeness property. And this is what we have proved, that we are taking any Cauchy sequence and then we are proving that it is a convergent sequence converging to some function f, and then we show that the limit is also in that space. Right? So complete means any Cauchy sequence converge and the limit is also in that space, the underlying space.
Okay, sir.
Okay. Okay. Okay, so now we have proven that. So as I mentioned in the last session, that okay, so why we are reading this convolution. So I have said you that it has a good property, that if the function is continuous and it has a compact support, okay, so if it is not differentiable, then if you mollify it, then you will get the regularity of what. So if you are mollifying a function, so suppose f is not differentiable or not continuous even, so if you mollify with if a function g which is infinitely c infinity, that is it is infinitely many times differentiable, then this convolution is also infinitely many times differentiable. Okay, so this is what I have said. Now this is the main requirement, but if you choose this g in a particular form, okay, then you can have many approximation result as well. Okay, so this g will be called a mollifier. So I'll say what the mollifier is. So it is a exponential function defined in a certain form. Okay, we'll see that. So so we'll choose this g in a particular fashion so that this g convolution f will have good properties and it will approximate this f. Okay, so let me just go directly to the result. So what it is, okay, so this is what you already know, that convolution of any function with with a smooth function with compact support. So you know, so when you have to do the convolution, just take one of the function to be compactly supported. So then this function will also be smooth. So if f is if f is any function, and if you take any cc function, then f convolution g is also cc, and if you take f to be cc infinity, then f convolution g is also cc infinity. Okay, so that's all this says. But for getting the approximation result, we need to specify what type of g we want to study. Okay, so before going to that, let us see this simple example. So consider this function f of x to be exponential of minus 1 by x square when x is greater than 0, else it is 0. Okay, so this function is infinitely differentiable. Okay, so I'll prove this, but in the just after stating about this one, so I'll just prove this property soon. So just assume for now that this function, so you can clearly see that if x is greater than 0, so suppose this is 0, so you can clearly see that in this region, because exponential is c infinity function, in this region f is c infinity. Even when x is less than 0, the function is 0, so constant function is infinitely differentiable. So here also it is c infinity. But the main question is, what about 0? Right? So the main doubtful point is 0. So at 0, whether the function is infinitely differentiable or not, that is the question. Okay, so in fact it is. So I'll show that this is c infinity function, but this is not compactly supported. And as I mentioned here, that the function we need to, so if f is any given function, and if you want to mollify g convolution f, so this g function has to be compactly supported, and whatever regularity you give, this will be also cck. So if k is 1, this is cc1, if k is 2, cc2, if k is infinity, this is cc infinity. Okay, so this g has to be compactly supported. So for the mollifier, so this was our first guess, that okay, this is a c infinity function. Now in the second step, what we want to do, we want to make it compactly supported. Okay, so what we do a bit of rescaling and consider this function. So a is given to be a parameter, so rho of a is exponential of minus a square by a square minus x square when mod of x is less than a, and for mod of x greater than equal to a, the function is 0. Okay, so it is like minus a, in this region the function is 0. Okay, and in this region some exponential thing is there. Okay, depending on a, so as you make this smaller, the function will also change accordingly. Okay, because the function is also depending on a, this a. Okay, so the way I'll prove that this is c infinity function, in the similar way you can prove that this is also c infinity function. So here doubtful points are 2. So here you have to check differentiability at minus a and a. Okay, so and note that here the support is compact, that right. So the support of f is actually minus a to a. Right? This is the support. Okay, so now I'll prove that this function f is a c infinity function. Okay, so as I've explained that you don't need to worry about the other points, so the only point to worry about is x equal to 0. Okay, so first let us check that f is continuous at x equal to 0 or not. Okay, so the first thing is limit, so f of 0, you know f of 0 is 0. Okay, so to show that limit x going to 0, f of x is equal to f of 0, and which is 0. So this is what you want to show for the continuity. Okay, so limit x going to 0 plus, so if you go from negative side, the function is taking the value 0, so this is obviously 0. Okay, now let us see what happens when you come from the positive side. Okay, f of x, so this is limit x going to 0 plus, and f of x is exponential minus 1 by x square. So this limit, if you see that as x goes to 0, this 1 by x square goes to infinity, and e raised to the power minus infinity will be 0, right? So this limit is 0. So this shows that f is continuous at x equal to 0. Okay, now I'll check that f prime 0 exists. Okay, so the next goal is that f prime of 0 exists. That means f is differentiable at x equal to 0. And so that is f is differentiable at x equal to 0. Okay, so now let us see the proof. So let us try to calculate this thing, limit x going to 0 minus f of x minus f of 0 by x minus 0. So this f of 0 is 0, and as we are talking about x going from negative side, so this function is also 0. So this is 0 by x. So limit x going to 0 minus, this is 0 by x, which is 0. Okay, so this is fine. Now let us check limit x going to 0 plus f of x minus f of 0 by x minus 0. So limit x going to 0 plus f of x is e raised to power minus 1 by x square, and this is x. So now we'll have to calculate the limit. Okay, so just try to observe the property of exponential. So from here, I mean, if you know exponential function well, you know that this, so this is also going to 0, right? So e raised to power minus 1 by x square goes to 0 as x goes to 0. Okay, so this is clear. So it is 0 by 0 form. Okay, now you already know that exponential decreases faster. The growth of exponential or the decay of exponential, depending on it is exponential x or exponential minus x, you know that the exponential is more, I mean, it grows faster or decays faster. So that's why you know that the limit will be 0. But anyway, if you need a proof, I'll just give. So I mean, you see that this exponential of x, you know that this is greater than equal to x, right? So this would imply the exponential of 1 by x square is greater than 1 by x square, and this would imply that x is greater than equal to 1 by x time exponential minus 1 by x square, right? So I am just doing the cross multiplication. So this function, okay, is less than equal to x, right? So this is less than equal to x, and this is obviously greater than equal to 0 when we are talking about, when we are coming from, so when we are talking about x belonging to 0 infinity. Okay, so this we already know that this will happen. Okay, so now if you take limit x going to 0 plus, this is going to 0, this is going to 0. So by Sandwich theorem, you know that limit x going to 0 plus 1 by x exponential minus 1 by x square is 0. Okay, in fact, what you can prove that any polynomial, so here what we have proved this thing, but you can in fact limit x going to 0 plus of 1 by x raised to the power let's say k exponential minus 1 by x square is 0 for any k belonging to natural number, and you can use the similar sort of argument. Okay, so and this reason is also quite valid because you know exponential decays faster or grows faster. Okay, so that is the reason that this will not be a big factor, right? And it's clear from the expression also, you know that exponential of x is 1 plus x square plus by factorial 2 plus this. So exponential of x is always greater than equal to any polynomial growth. Okay, so this is always decays faster. Okay, for any case, I mean, this is the reason you have this, that the limit is 0. So we have proven that this both the limit coincide, right? So left hand limit and right hand limit coincide. So this implies limit x going to 0 f of x minus f of 0 by x minus 0 exists, and f, so this is the limit is f prime 0 and this is 0, right? In a similar way, so using this fact, you can prove that f a for any k, the kth derivative of f will be 0 for all k belonging to natural number. Okay, so it is differentiable at x equal to 0. And in a similar way, I mean the way, so what is the f prime? So before going to this, let me write what is f prime. Okay, so f prime of x is, so e minus 1 by x squared derivative for x greater than 0, and x less than 0 it was 0, and at x equal to 0 also this is 0, right? So f prime is this one. Now in a similar way you can show that the f prime is continuous, and you can again differentiate this, okay, in a similar fashion. So using this result you can prove that f k at 0 will be 0. Okay, so using similar analysis, one can prove that f belong to ck omega for all k belonging to n, and this implies it was r, right? F belong to c infinity r. Okay, so this function exponent, this function is infinitely many time differentiable. In a similar way you can show that this is infinitely many time differentiable. Now this will motivate you, I mean this is what we wanted. So we wanted c infinity function, and the support has to be compact, so we have obtained that property. Okay, so we'll define this mollifiers in a similar way. So I mean the only change you see is this one. Okay, and this is done just to make sure. So because of this condition, what you can prove, that integral if you take rho epsilon, okay, over r, so this integral will be 1. So this is added for that purpose, and this is just to simplify the computations. I mean later on when you prove certain theorem, you will need this property. So that's just the constant which has been added here. Okay, so okay, so let me just try to explain you how it looks. So see, this is minus epsilon, so I am telling in r. Okay, so for n equal to 1. Okay, so suppose this is minus epsilon to epsilon, and this is 0 somewhere. What it says, that outside epsilon region, when mod of x is greater than equal to epsilon, the function is 0. So this function is 0. Okay, and in this region this is exponential type of function, and also so this rho epsilon is c infinity. Okay, okay, and the support is also compact, so c infinity function. Okay, so this function has to start from here somehow, and this is the property of exponential, that this will it will look like this. Okay, now you know that the integral is 1, so that means that this region, okay, so the value or the area is 1 unit, so this is 1 unit, so integral of rho epsilon is 1. Now suppose you make this epsilon smaller, so now make this epsilon here, so minus epsilon and epsilon. Okay, so so let's say this is epsilon 2 and this was epsilon 1. Okay, so you know that outside this region the function is 0. So here the function is 0, here the function is 0. Okay, and in this region, this integral, you notice that the rho epsilon 2 will also be 1. That means the area should be same, right? So this will be a bit higher, right, just to make sure that the area is 1. Maybe a bit larger. Okay, so something like this, so that again this area, this rho epsilon 2 is also 1. So this is how this function behaves, this rho epsilon. So as you make this epsilon smaller and smaller, so as epsilon goes to 0, this integral will still be taking the value 1, right? So isn't that surprising? That so what it's saying, that rho epsilon is 1 for all epsilon, but as epsilon goes to 0, okay, to the function what it converts, this integral is also 1, but from the picture you can see that this picture will compress to one point. Okay, so if you know, it's good that this function is nothing but this f is Dirac delta. Okay, so so let me write it somewhere, that this rho epsilon converges to Dirac delta, and this convergence is not pointwise. Okay, so this is in the sense of distribution. So if you know what it is, the sense of distribution. Okay, so if you don't know about the distribution, you don't need to bother about it. So this is what it happens. Okay, so this Dirac delta, so this is the Dirac delta at x, it takes the value 1 as x equal to 0 and 0 when x is not 0. Okay, so this is the Dirac delta. Okay, so this is something extra comment what I wanted to put it here. So this is the mollifier. Okay, so this mollifier is a smooth CC infinity function, and this converges to Dirac delta in the sense of distribution. Okay, and okay, actually this is okay, leave it. So I mean, from this, I mean, this results are enough to make you understand, but actually this result gives you this type of result, this approximation result. Okay, so for that, actually you have to understand what is this quantity. Okay, I mean, you don't need to worry about this. So let us just try to see the result what you have in hand. So what is the benefit of this mollifiers? Okay, so I said that, okay, it is C infinity. So one thing you can say, that if f is any function, so f is any function that is given to you, then this rho epsilon convolution f is C infinity function. So this is a C infinity function. But what are the other properties of this convolution? Okay, so it in fact approximates the function f. That means the rho epsilon convolution f converges to f in appropriate sense, that we'll see depending on what f is. Okay, so let me just quickly state the results. So the results are, suppose f is a continuous function, then this rho epsilon f converges to f pointwise. Okay, so this rho epsilon convolution f at x will converge to f of x as epsilon goes to 0. Okay, if f is a continuous function with compact support, okay, in that case this convergence is not just pointwise, but it is uniform convergence. This means that rho epsilon convolve with f minus f sup norm goes to 0. Okay, or infinity norm. Okay, so this goes to 0. The third thing says that if f is a continuous function with compact support, then I mean the similar sort of thing, then rho epsilon convolution f converges to f in LP for all p in this 1 to infinity. Okay, and this is the case of infinity. So I mean p equal to infinity is this one. Okay, so this is what I have written, that p equal to infinity is nothing but case B. So this says that rho epsilon convolve f minus f with p norm goes to 0, and this is for p equal to infinity. Okay, now if a function f is in LP, so till now we were dealing with when f is continuous function with either with compact support or not. Now let us see when f is in LP, f is a LP function, then again this rho epsilon convolved with f will converge to f, okay, in LP. But this is not true for p equal to infinity. Okay, so this is strictly less than infinity. P is strictly less than infinity. Okay, so for any LP function, this rho epsilon convolution f converges to f in L infinity in LP. So you can see that for any LP function you get a smooth function which approximates that function, right? So this rho epsilon convolution f is C infinity function. right? So any LP function you are approximating by C infinity function, right? So this is the advantage of this mollifier, that you can approximate any LP function using C infinity function. Okay. Okay. So now, uh, so this is what I mean. It's the same thing. This is written in another words, that if omega is any open subset of Rn and p is less than infinity greater than equal to 1, then the space of C infinity function with compact support is dense in LP. Okay, and okay, so this is, I mean, here you just have C infinity function, but the result is much more true, that CC infinity function is dense in LP, right? Here what you proved, that C infinity function is dense in LP. Okay, and here I am saying that CC infinity function is dense in LP. Okay, so are these statements clear to you? I mean, these are some result which you can prove using the definition of convolution and all. I mean, just either DCT or something like that. Okay, so the proofs are not that difficult. You just need to understand the convolution well. Then you can do these proofs by yourself. Okay, so is this fine?
Yes, sir.
Okay, I mean, if everything is fine so far, then I'll move to the problem section. So do you have any doubt, I mean, so far, whatever I have said? Okay, so everything is fine. So let's proceed to some problems. Okay, so okay, so let f be an LP function. Okay, then what you have to prove, so this is strictly less than infinity. You have to prove that the integral of f on this domain, that is mod of x greater than k, is equal to 0 as k goes to infinity. Okay, so I mean, it simply says that if you have this minus k and this is k, so as k goes to infinity, that is as this domain goes to infinity. Okay, so I mean, this is the region. Okay, so this is the region. So as k goes to infinity, that means this is shrinking. Okay, so this is going apart, this minus k and k are going apart. So if you take the integral in this region, so suppose you have a LP function, so this is some LP function, then what it says, okay, so in terms of area I am saying that the area covered in this region will go to 0 as k goes to infinity. Okay, so it's like this one. So if you want to understand, so you know that if a series, so you know that integration is generalization of series, right? I mean, for counting measure, you know that integration is nothing but summation. So you can think in this way. So you know that when this series xn is convergent, okay, n equal to 1 to infinity, you know that xn from n plus 1 to infinity, this goes to 0 as n goes to infinity, right? Similar sort of thing is here, that I mean, as k goes to infinity. Okay, so if you want to just analog of this, so take 0. So if a function f is in LP 0 infinity, then the area, so just concentrate on this part, then this area will go to 0 as k goes to infinity. Okay, analog to this one. So this is something which is natural that you expect, so you have to prove this one. Okay, okay, so let us start the proof. Okay, now to understand this, I mean, this is simply just an application of DCT, to be more precise. So you can understand this integral. So let me rewrite this integral. So mod of x greater than k, mod of fx raised to the power p dm1x. Okay, you can write it as chi of mod x greater than k, mod fx raised to the power p dm1 of x. Right, this you can write. Now let us try to understand what this function is. Okay, so let us define this as g of x. Okay. So this g of x, I mean, okay, or let us directly deal, and let's not include more notation. So this chi of mod x greater than k, x mod of f of x p. Okay, so this function goes to 0 as x goes to, sorry, as k goes to infinity, right? Because this function is going to 0 as k goes to infinity. Is this clear that this goes to 0 as k goes to infinity? Right? I hope this you understand, right?
Sir, can you please explain?
Okay, so I mean, so maybe I'll just explain by pictorially. So this means that minus k to k, the function is taking the value 1. Sorry, here the function is taking the value 1 and here it's 0, right? Now choose some x. So maybe choose some x from here. Okay, so now as the k increases, that means the area where the function is 0 is this one. So let's say this is another k which is larger one. So and the graph would be like this, right? So as k increases, the x, whatever x you choose, it will come in the region minus k to k. Okay, so in this region the function will be 0. Okay, so the limit will also be 0, right? So you understand the graph. So whatever x you fix, if x is here, then already it is 0. Okay, so you just need to make sure. So it's just the Archimedean property that for x in R there exists a k in natural number such that x is less than equal to k. Right? So for each x you will, and now for after this k, now this is always less than equal to any natural number n, right? So I mean, so as n k goes to infinity, this x will come in the range minus k to k where the function is taking the value 0, right? Because this function is 1 after the k, I mean outside minus k to k. Okay, so this is pointwise converging to 0. Okay, if you want I can keep it here somewhere. Okay, so this converges to 0 as k goes to infinity, and also, so this is one property. The second property is that this function chi of mod x greater than k if x and this mod of fx raised to the power p, this is bounded by mod f raised to the power p, because this is bounded by 1, so this is fx raised to the power p, and you know that this f is in LP, so, and mod of fp is integrable, so because f is in LP, integrable, so by DCT this integral of chi mod x greater than k x mod fx p goes to 0 as k goes to infinity, right? And this is what you wanted to prove, right? Yeah, is this clear?
Yes, sir.
Okay, so this was about when p is between 1 and infinity. What about p equal to infinity? I mean, this is very easy, but can you give me one counter example? So the example is that f, f should belong to this L infinity space, but this integral limit k going to infinity mod of x greater than k mod fx raised to the power p. Okay, okay, this does not make sense for p equal to infinity. Okay, you can leave. So this does not make sense for, because this fx raised to the power infinity does not make sense, right? Okay, so you can cut this question. Okay, yeah. Okay, so this question does not make sense here, right? Okay. Then you can do this. Okay, so this was about the behavior, and as I said that this is equivalent to the series thing what you have seen in analysis course. Okay, now let us move to the next problem. So here you have been given a function fk, a sequence of function fk, such that fk converges to f in LP space. Okay, in LP, that means this fk minus f p norm goes to 0, like this. Okay, so this is by definition. Or you can say that fk converges to f means that norm of, so okay, you can write it here as well. So fk converges to f in LP also implies that norm of fk p norm converges to norm of fp, okay, as k goes to infinity. Okay, okay, so this is some implication of this fk converging to f. Now you have to show here that fkx raised to the power p in the region mod x greater than equal to k will be converging to 0. Okay, similar sort of question, but here now this is not a function, just a fixed function, but this is a sequence of function. K is here also, so that is the difference, that k is here also and here also. And because of this presence of k inside the integral, you cannot use the DCT type of result. Okay, directly at least. Okay, so the proof will go in this way. The reason being, so here you see, you can say here at this level that this product of these two functions will go to 0. But when you have fk here, you cannot say, because about fk you have not been given information that fk converges to some function f. So if it was given, so if you say that fk converges to f almost everywhere along with this, so plus this, then you can probably use the same proof. What I have done here, similarly you will get the result, no problem in that. But here the problem is that point-wise convergence you don't have in this question. You have that fk converges to f in LP, you don't have that fk converges to f point-wise. So that is the problem. Okay, so you cannot use DCT. So what you can do, so you can go in this way. Okay, so let me start the, okay, so let us try to break this integral. So you know that f of this p norm over r, I can write it in two ways. I can break it up in two factors. So mod of x greater than k, mod of fkx raised to the power p, and then plus mod of x less than equal to k as mod fkx raised to the power p, right? So this I have just broken this integral in two parts. Now from here I can write this. So what I wanted to evaluate is this one, so let us keep this here. So f k x raised to the power p is equal to kx raised to the power p. So this is over a mod x greater than k, this is over r, minus mod of x less than equal to k fkx of p. Okay, so let me call this star. Okay, now you have to prove. So what you want to prove, that this limit of this thing goes to 0. This was your question, right? That this, so you have to prove that this goes to 0. Okay, so let us first note one thing, that this, you know that fk converges to f in LP. So this fk, so I think I mentioned here, so this one. Okay, so fk p norm will converge to f of p norm. Okay, as k goes to infinity, and this implies that mod fk raised to the power p converges to mod f raised to the power p. Okay, so this is over R. So let us say this is 1. Okay, so this quantity, you can say that this quantity goes to this quantity, mod of f. Okay, now I will prove that this also goes to this. Then we are done, that the difference will be going to 0. Okay, so my next claim would be that x mod x greater than k, okay, of this, sorry, less than equal to k, of this fk x raised to the power p converges to f raised to the power p over r. Okay, so that's our game. So as k goes to infinity. So let us try to prove this. Okay, so so what I'll prove, so okay, so let us see. So okay, I think I should not write this directly. So what I can write, I'll not prove this directly. So what I'll prove instead is if, okay, let me just write the proof, then it will be clear. So I'll prove this one. So fk and then chi of this mod x less than equal to k will converge to f in LP. Okay, so this is what I want to prove. Okay, and this will give you this one. Okay, so okay, so to prove this I have to evaluate this integral. So mod f chi mod x greater less than equal to k of minus f, so this is x, f of x chi of x minus f of x raised to the power p. Okay, so this is equal to what I can do. Okay, so again I can break it. Okay, so what I'll do, so I'll break it in two parts. So one would be over x less than equal to k, and the other would be the complement. Okay, so now this is the function. So let's say this is g and this is f. Okay, so okay, so this is, I mean, so I'll just write in a this. Okay, let us carry this notation. This is this, and so why I'm doing it will be clear. So chi of f of x, chi of x less than equal to k minus f, and then plus this is mod x greater than k mod f chi of mod x less than equal to k minus f raised to power p. Okay, so why I'm doing this, because this function, okay, is depending on the domain. So this was over whole R. Okay, so if you notice, this function on this domain is taking the value 1, right? Okay, I forgot this k, I guess. This is fk, this is fk, this is fk. Okay, so this is taking the value 1. So this is nothing but mod x less than equal to k, this fk of x minus f of x raised to the power p, plus, now in this region when x is greater than k mod x, then this is 0, right? So that is why this integral will be mod of x greater than k mod of fk minus f raised to the power p. I mean, so there will be no fk, sorry. So this is mod f raised to the power p. Okay, now this you have proved here, right? So in the first problem you showed that mod x greater than k, sorry, not this one, mod x greater than k, integral of mod f raised to the power p will go to 0 as k goes to infinity. So this term goes to 0 as k goes to infinity, and this is by the last problem. So right, and about this one, if you see, I can write that this is dominated by okay, so I cannot, this I can write this is less than equal to the whole integration over r fk minus f raised to power p plus, okay, so I mean again this quantity, maybe I should copy this, just a second. Okay, so I am just dominating. Now you know that this is nothing but fk minus f lp norm, right? So this is nothing but fk minus f lp norm and raised to the power p, right? And you know that this also goes to 0. This was given to you that f converges to fk in lp, so this goes to 0. So this quantity is goes to 0, right? So this implies that f characteristic of mod x less than equal to k converges to f, right? I mean this was that this g converges to this f in lp, so this f in lp of r, right? Yeah, so when this converges to this function, so the norm converges to this, right? So this implies that the LP norm of this function f chi x is then equal to k converges, sorry, mod f raised to power p converges to mod f raised to power p, right? And this is nothing but mod x greater than equal to k mod f raised to power p. Right, so what we have proven that if you integrate the function f, I mean mod f raised to power p over compact set, so on this ball, so this is radius k, right? Or in r it's just the interval minus k to k. So as k goes to infinity, this integral, I mean this area converges to the whole area, and this is what you expect. So, this is not a surprising result. So this is done. So in this star, so this is, let's say, 1, then this is 2. So if you put this in star, so star, if you by 1, you know that this converts to integral of f raised to power p, right? This quantity converts to integral of f raised to power p, and this quantity by 2 also converts to integral of mod f raised to power p. So this whole difference, right, this whole difference converts to 0 as k goes to infinity. So using 1 and 2, using 1 and 2 in star, we get limit k going to infinity, mod x raised to power k mod fkx raised to power p d m1x is 0. Okay, okay. Okay, so is this clear to you? Right, so you cannot apply DCT directly here, so you have to basically split it in two parts and you have to prove the convergence independently. So both will converge to integral of f raised to power p, and hence the difference will converge to 0. Okay. So now let's move to the next problem. Okay, so here what we will prove that this, so let me state something before going to the proof. So this C0, what is C0? C0 is the space of sequences, so it belongs to Xn, collection of all sequences such that the Xn goes to 0 as n goes to 0, as n goes to infinity. So the sequence converges to 0. So we consider all those sequences. Okay, these are sequences in R. So these are real sequences. So this is the space C0, and with this C0, if you give this space, okay, so this is a normed linear space. I mean, this is a linear space, so I mean, this is quite easy to see that this is a linear space, right? Because if xn and yn converge to 0, then xn plus yn converge to 0, and if xn converges to 0 and if you multiply with any constant c, then c of xn also converges to 0. Okay, so it is clearly linear space, and it is, you are given this norm, so this is normed linear space. And what is this norm? So if you have a sequence, okay, so let x equal to xn be a sequence, then norm of x infinity is equal to the maximum n belonging to n, okay, mod of xn. So this is the norm what you give. Okay. Okay, so this is the space what we will be studying. So what you have to prove, that this C0 space is complete. Okay, again similar sort of thing, that will take a Cauchy sequence and then we'll prove that it is converging in the space C0. And the second thing is that you have to prove that C0 prime will be equal isomorphic to L1. Okay, so the dual of C0 is L1. So even this is true in continuous setup as well, that C0, so C0 is the space what I defined earlier, so this is capital C0. If you take the dual, you will get L1 space. Okay, okay. So I'll prove this for a small LP spaces. Okay, but before going to proof, let me state some more properties or comment about this one. So you know that the dual of L1 is L infinity. Okay, so I don't think that you have seen the proof, but the proof will be similar to what you have seen for Lebesgue spaces. So this is analog to L1 prime is equal to L infinity. Okay, so this is true. Okay, and you also know that this L infinity prime is not L1. Okay, again the analog to, so you can find a counter example for that. So I have given an example for this one, that L infinity prime is not L1. Okay, that okay, so but what I am claiming here, okay, what I am claiming here is that C0 prime is equal to L1. Okay, okay. Now tell me one thing, that's what is C0 space? C0 space is a space of real sequences which converge to 0. Now since the sequences are convergent, it is bounded, right? So if I say x belong to C0, this means that xn converge to 0. This implies that the sequence xn is bounded, right? This implies xn belong to L infinity space, right? Okay, so this what did I show is that C0 is contained in L infinity. Okay, and you know that you can find a sequence which is bounded but it is not convergent. And I mean, forget about the converging to 0, but it will not be convergent. So this is not equal to L infinity, right? Okay, so L infinity is just the space of bounded sequences. So you can have a bounded sequence which does not converge to 0. So that's why this cannot be equal to L infinity. Okay, so now you just try to look at these things what I've said. So you know, so from here what you can conclude, that the dual of L infinity, okay, is contained in dual of C0 prime. Okay, and I will show this, that C0 prime is L1. Okay, and this will also, so L infinity prime cannot be equal to L1. Okay, because because of this thing. This is just another proof of saying that L infinity prime is not L1. But what I am trying to say here, that this is L infinity space, this is C0 space, okay, and the dual of C0, okay, I think I wrote another way around. So this is L infinity, this is C0, and the dual of C0 is L1. Okay, so the dual of L infinity is contained in L1, but it is not L1. Okay, so this L infinity prime is contained in subset of L1, but it is not equal to L1. Okay, so that was few comments that I wanted to make here. Now let us go to the solution of this problem. Okay, so change the color. Okay, so now let us go to the solution. Okay, so the first thing is to prove that the sequence, the C0 space is complete. Okay, so now let xn, okay, so why I am putting this n, okay, so I'll tell you. Okay, so for now just let xn be a Cauchy sequence in C0. Okay, so just try to understand what the sequence are. So suppose x1 is one member of C0, right? X2 belong to C0. Now this x1 is itself a sequence. So this x1 is like this, that x11, x12, x13. Okay, so this is the way I am representing. So this is a sequence. Again, x2 is belong to C0, means x2 is a sequence. So it's like x21, x22, x23, and so on. Okay, so this is the space of sequences. So each xn is a sequence. This xn is a sequence, but each xn itself is a sequence. So it is a sequence of sequence. Okay, okay, so okay, let it be here. So now you have a Cauchy sequence in C0. This means for epsilon greater than 0, there exists n in n such that norm of x, such that norm of xn minus xm infinity norm is less than epsilon for all n comma n greater than equal to n. Okay, so this is just the definition of Cauchy. Now this implies, okay, so this, what does this norm is? This is maximum or supremum. Is it maximum or supremum? Okay, so whatever. So xn k minus xmk. Okay, and k is from k belong to natural number. So this is the definition of infinity norm, right? The maximum of the sequences, the term of the sequences. Okay, so this is there. This implies that xn minus xm, the kth term of the sequences, is less than epsilon for all n comma n greater than equal to n and for all k belonging to n, right? This implies that the sequence xn, okay, so this is xn k x and k equal to 1 to infinity is Cauchy. Is a Cauchy sequence, right? Okay, I mean you might be confused by the notation, so okay, so let me give you brief explanation of what I'm doing. Okay, so let me just shift it a bit here. So see what I did, I chose a sequence xn x, so and the subscript is given. Okay, so this x1 is a sequence x2, x3 and so on, xn and dot dot dot. So this is a sequence what I chose in C0. So this is a sequence in C0 space. That means each of the xi's are itself a sequence. So this is a sequence. So let me denote it by, so I'll just use an bracket to denote it. So it is x11, x12, x13 and so on, right? So this is a sequence. This x2 is again a sequence. So x21, x22, x23 and so on. x3 is also sequence. So x31, x32, x33 and so on. In a similar way, this xn is also sequence xn1, xn2, xn3 and dot dot dot. Okay, so this is how the things are. Okay, so what I did, I said that these xn's, these are Cauchy, and from there I derived that for each k, so for each n, so let's fix this n. So n is the upper one, right? So for each n, it's Cauchy sequence for each n. Okay, so let's say n equal to 1. So for n equal to 1, this is the sequence x1, x2. So for n equal to 1, this is x11, x12, okay, x13. Wait, just a second, I am also. Just a second. So this is xn, k is Cauchy, right? Sorry, I think I wrote it wrong. So this is, so this is true. So this is true for each k, right? For each k. So for each k, the sequence xk n, where n is varying from 1 to infinity, is Cauchy sequence for each fixed k, for each k in n, right? Okay, now this is correct. Okay, so what I am saying, that if you fix n equal to 1, that means this one. So n equal to 1 means, okay, sorry, k equal to 1. So k equal to 1 means this vertical thing. Okay, so for k equal to 1, this one x1, x21, x31, xn1, like this sequence is Cauchy. Okay, so this is Cauchy. Again, this for k equal to 2, this sequence is Cauchy. So for each of them, this sequence of real number is Cauchy. Okay, so it will converge. Okay, so I mean, you know that any real sequence, any Cauchy real sequence is convergent. So this implies that x n k, n equal to 1 to infinity, converges for each k. So let x and k converge to xk, so for k belonging to n, as n goes to infinity. Okay, so is this clear? So what I am saying, that this sequence will converge to, let's say, x1, this will converge to x2, this will converge to x3. Okay, so this is what I am saying. So did you understand this picture?
Yes, sir.
Yeah, okay. Okay, so you got that each of the vertical thing is convergent. So now define, so now let's say this is your x, so define x, so you call this sequence, okay, as x. So define x equal to xn, or maybe I will write x1 x2 x3 dot dot dot. Okay, so this is your x. Now the claim would be that this sequence xn, okay, so the claim is that you have to prove two things. Okay, so maybe let me, okay, so claim a is that this sequence xn converges to this x, okay, in L infinity norm. The second thing is that this x what you got should be in C0, right, that the limit should be in C0 space to prove the completeness. Okay, so let us start the proof. So let us try to prove the first one. So if you try to, so you have to prove that this norm goes to 0. Okay, so what is this? So this is maximum or supremum. I think it should be maximum. Everywhere I am writing, so you can take maximum, something like that. Okay, this is maximum k belonging to n mod of xn k minus xk minus xk, and you know this quantity, okay, for each k you have proven that this xnk converges to xk. That means this quantity goes to 0 as n goes to infinity for all k, right? This is true for all k. So this means the maximum of whatever you got will always, this quantity will always converge to 0 as n goes to infinity, and this proves that norm of xn minus x infinity norm will go to 0 as n goes to infinity, right? So we have proven that xn converges to x in L, in this L infinity norm. Okay, the second thing what you need to prove that this x will belong to C0. That means xn will converge to 0. So I mean, so, okay, so that is, so you can rewrite this. This is xn or xk. So don't confuse with k and n. It's just a notation. Belong to C0. That is, this xk converges to 0 as k goes to infinity. So this is what you have to prove. Okay, so again, I mean, the similar to what we have proved here, I mean, at the beginning of this session when we were proving that this C0 with infinity norm is complete. Okay, so the same idea will be applied here also. Okay, so let epsilon greater than 0 be any real number. Okay, now you know that, so the first thing what you know is that xn belong to C0 for all, right? This is the sequence what you started with. So this implies, okay, so okay, before going to this you can write it, but okay, it's better to start with the sequential thing first. So you know that this xn converges to x in L infinity norm, right? So this implies that mod xn minus x infinity is less than epsilon by 2 for all n greater than equal to capital N, right? So here it's xn, so there exists n, says that this, okay, so this says that x capital N minus x infinity norm is less than epsilon by 2. Okay, and this implies that, so what is this norm? So this is maximum of k belonging to n mod of x n k minus xk. Okay, so this is the maximum which is less than epsilon. So each of the term x n k minus xk will be less than epsilon, right, for all k. And this, okay, so this is, let's say this is one of the equation. Okay, uh, okay, and now the second thing is that you know that this x capital N belong to C0, right? So each xn belong to C0. In particular, this x capital N belong to C0. This implies that mod of xn, okay, I mean xn belong to C0 means xn converts to 0, right? So that is x capital N converts to 0 as k. So this xn is nothing but this type of thing, xn k. Okay, so this xn k goes to 0 as k goes to infinity. So this means that xn k, I mean there exists k, or in belonging to this natural number capital K, such that mod xn k is less than epsilon by 2 for all k greater than equal to k, right? So it's at k naught. Okay, so now what we wanted to prove that this xn converts to x, we wanted to prove that x belong to C0. That means this xk converts to 0. So let us try to estimate this xk. So mod of xk by triangle inequality is nothing but xk minus xkn plus xkn, right? You know that this is less than epsilon by 2 for all k, and this is less than epsilon by 2 for k greater than equal to k naught, right? So this implies that mod of xk is less than epsilon by 2 for all k greater than equal to k naught, right? So this proves, this implies that this sequence x equal to xk belong to C0. Sorry, this will be less than epsilon, right? So this proves that the limit x will also be in C0 space. Okay, okay, so this was the first part which proves that the C0 space is complete. Okay, so do you have any doubt so far? Okay, if everything is fine, then let us proceed to the next part. So next part is you have to show that C0 prime is isometrically isomorphic to L1. Okay, so let us begin the proof. So again, this proof is also, I mean, in a similar spirit of what you have seen when you are proving that the dual of LP is LQ or LP prime. So the proof will go in the same manner. Okay, so let us try to do step by step. So the first thing what we need to prove, so as we proved there, right? So what we proved that when we wanted to prove that LP prime is isomorphic to LP prime, so what we chose, we took one G from LP prime and then we defined TG to be F times G. Okay, and then we proved that this TG belonged to LP prime, right? I mean, this was the first thing. Similarly, we will do it here. So choose, so what we want to prove is isomorphic to L1. So let Y belong to L1, similar to let G belong to LP prime. Okay, and define this phi y of x to be summation x n y n equal to 1 to infinity. So it was similar to the integral fg. Okay, so this is for all x belonging to c0. x बराबर xn belonging to c0. Okay, so this is the definition of phi y. Now my claim would be that this phi of y, this phi y belong to this c0 prime. Okay, so the claim is that phi y belong to c0 prime. Okay, that means it is a continuous bounded linear functional on c0. Okay. Okay, so phi y, so let us try to, so first we want to prove that it should be linear. So clearly by definition phi y of x, or I mean x plus z, okay, is equal to summation xn plus zn yn n equal to 1 to infinity, and this is equal to summation xn yn plus summation zn yn, and this is equal to phi y of x plus phi y of z. Okay, so it is, and also you can prove that phi y of cx is equal to c times of phi yx. So this is linear. I mean the phi y, so this phi y is linear functional on c0, but we want to prove it is a continuous linear function. So phi y of x is nothing but summation xn yn. Okay, now you can take the infinity norm, so you can take the maximum of xn outside because x is in c0. Okay, so you can take x infinity norm, and then you have, okay, so first step would be to take the modulus inside and then take the infinity norm. Okay, so if you want you can add one more line, mod of xn mod of yn. So you can take the infinity norm outside, so this is norm of x infinity, and then you have summation mod yn n equal to 1 2. So this is L1 now, right? So y small L1 now. Okay, so this proves that this operator norm of phi y is less than equal to norm of y1. Okay, so let's say this is star 1. Okay, so this is a continuous linear function. So this proves, hence phi y belong to c0 prime. Okay, so we have proved that if you take any L1 function, so y going to phi y, okay, it's injective, but you can prove the uniqueness also. I mean, okay, I mean by definition it's unique. So this map y going to phi y, is well defined. So let me write this. So t from L1 to C0 given by t of y equal to phi y is well defined. Sorry, this is C0 prime. Okay, so this was step 1 where we choose L1 function and we showed that using this L1 function we can generate a linear functional on C0. Okay, but we have to prove the other way around also, that if we choose any linear function, that is, so the second step. Okay, so if you want, okay, let's not write in terms of step. So my another claim would be that t is surjective. That t is surjective. Okay, so what does that mean? This means that if I choose any linear functional from here, okay, then I should get a L1 function such that t is equal to t, I mean, sorry, the phi. So let me write it more precisely. So let so claim to be for phi belonging to C0 prime. Okay, so any linear continuous function you choose from C0 prime on C0, there exists y belonging to L1, okay, and this is unique. There exists unique y belonging to such that this phi is equal to phi of y, okay. So that would be our second claim, okay, that any, so that is, in other words, you can say that that is T is surjective, okay. So let us try to prove this claim. So we will have to find y from L1, so we have to construct some y, okay, and this is how it goes. So for what you do, you just choose the standard basis, okay. So let En, okay, so I'll write what this En is, be a sequence in C0, okay, where En is like this. So E1 is like 1 0 0 0 like this, E2 is like 0 1 0 0, E3 is like 0 comma 0 comma 1 0 0 0 and so on. So understood that En will be 1 at nth entry, okay. So altogether what I can write is where En, okay, so I mean, so En is a sequence, right, Enk. So satisfy Enk is equal to delta Kn, okay. And more, I mean, for understanding purpose, you can understand in this way, right? Okay, so when k is equal to n, that is the kth term of the sequence will be equal to 1 when k is n, otherwise it is 0, okay. So this is what this Kronecker delta means. It is 1 when k is equal to n, otherwise it is 0, okay. So this sequence is obviously in C0 space because it is converging to 0, okay. So now, so define y of n to be phi of En, okay. So this is the definition, okay. Now the first thing what we want to make sure, so I mean, my claim would be to show that this yn sequence is in L1, okay, and this T phi is equal to phi of y, okay. So let us first show that phi is equal to phi of y. So define y in this, and now, and let y is equal to this sequence yn, okay. So I'll have to prove two things. So I will just write here, need to show that phi is equal to phi of y and phi and y belong to L1, okay. These are the two things what we want to prove, okay. So let us start with this one, phi is equal to phi y, okay. So first notice this thing. So consider x as a, I mean, this type of thing. So let x be of this type of sequence, that x1 x2 till xn it is, but after xn it is 0, okay. So this type of sequence you consider, okay. More precisely what I can write is, this is nothing but summation k equal to 1 to n xn and then En, right. So this is, I mean, this is clear, right. So x1 times 1 0 0 like this, plus x2 times 0 1 0 0 plus xn type, so this is xk times or xn times 0 0 1 at nth place and then 0. So if you sum it up, you will get this type of sequence, okay. So this is another way of writing it, and why I am writing it is also, should also be clear just now. So let take x to be this type of function, this type of sequence, okay. Then you notice that phi y of x, so by definition what is phi y of x is xn comma yn n equal to 1 to infinity, right. And you know that, sorry, okay, So this is by definition. Now you know that the xn's are 0, or let me write k. So this k is varying from 1 to infinity. You know that this xk is 0 after n, right? So this is nothing but xk yk from k equal to 1 to n. Okay. Also, if you evaluate this phi of x, okay, so phi I can x is can be written in this form: k equal to 1 to n xk and then ek, right? So since phi is a linear functional, I can take the summation outside. So k equal to 1 to n, xk is a real number, and phi of ek, right? What is phi of ek? Phi of ek, you see, I have defined it to be yk. So I mean, right? So this is summation xk and this is yk, and k equal to 1 to n. Now you can clearly see that phi of x is equal to phi y of x. So phi of x is equal to phi y of x. Okay, and this is true for what type of function? So for x belonging to, so okay, so you can, so let me define some space here. So maybe here I should write, so see, the main thing what I'm saying, trying to say that this is true for this type of sequence. Okay, but see, this x equal to 1 by n is a sequence which converges to 0. So this 1 by n belong to C0 space, but this is not of this form. Okay, so this type of a space is called C0 space. So C00 space, you can define it as a sequence x, so this sequence xn such that xn is equal to 0 for large n. I mean for n greater than equal to some n naught. Okay, so what it says that it is so you have heard this concept, right? So I mean, it is not a constant, but it is almost constant. That is, after some point it is becoming a constant sequence, and this constant sequence is nothing but the 0. The constants here are 0. So this is called C0 space, I mean C00 space, and you can see that this is nothing but this is a strict subset of C0. Okay. So this phi of x is equal to phi y of x for all x belonging to C00 space. Okay, and this C00 space is dense in C0. Okay, so there are 3 points. So this is dense, and phi and phi y are continuous on, I mean, we cannot say about phi y. Okay, so just a second. Okay, so actually, okay, so for now, so I think I should first prove this one. So maybe let me write in this way. Oh wait, this one is true. So for now you assume this one. Okay, so need to show this 1 and 2. So we are proving 1 first. So I mean, this should be 1 actually, so let me rewrite it. So 1 is to prove that y belong to L1, and the second one is to prove that phi is equal to phi y. Okay, so I am proving the second one first. Okay, and then I'll come. So for now assume, so assume it for now. So I mean, I should write here, so assume 1. Okay, so you assume that y is in L1. Now when you say y is in L1, you know that phi y is continuous. So are continuous on C0, right? So are continuous linear functional on C0. Functional on C0. Okay. hence, so using these statements, so what you can say, hence phi is equal to phi y on C0. So when two continuous linear functionals matches on a dense subspace, then it is equal on the whole space. Okay, and this you can prove. So I mean these are the, because of these three conditions you can conclude this. Okay, so I mean this is what we in general also use. Most of the time we just check for the dense subset. If for the dense subset it is true, then we say that it is true for the whole space if they are continuous linear functional. Okay, and this I think is due to this Hahn-Banach theorem. Okay, I'm not sure about the name, but either it is you can derive it from there, or Hahn-Banach theorem generally extends a continuous linear functional. But okay, I mean some corollary of Hahn-Banach you will get this. Okay. Okay, so you get that phi is equal to phi y on C0 space. Okay, so now what you need to do, so this, what you wanted to prove, that this one, that y belong to L1, and this is needed. So this continuous, phi y is continuous because y is in L1. So I will just write it, since y belong to L1. Now I will prove that y belong to L1. So now to show y belong to L1. Okay. Okay, just a second. Maybe I'll just put hash. So this was step 1 sort of. This was step 2. Okay. Now I'll show that y belong to L1. So this, I mean this is not that obvious, so you'll have to do a bit of manipulation. So what you need to do, so define some xn using this yn. So yn I have defined here, right? Yn is equal to phi of en. So using that you can define xn as yn by mod of yn by yn. Okay, if yn is non-zero, and if it is 0, then you can define it as 0. Okay, this is xn, and from using this you define this zn. Okay, so this zn is a sequence of this sort, x1, x2, x3 and so on. So this is again the same thing. So this is xk, ek, okay, it will be till xn and then 0 0, k equal to 1 to n. So you are defining this zn. Okay. Okay, then what you do, so here you need to make sure that this zn, you see that it is almost after certain state it is 0. So this zn actually belong to C00 space, and in fact you can say zn belong to C0 space. Okay, and if you take this infinity norm, okay, this infinity norm is maximum of k belonging to n, znk, right? You see znk is either 0 or it is some x size, and you see the norm mod of x size. So if you calculate mod of xn, it is either 1 or it is 0, 1 or 0, right? So this infinity norm of zn will be maximum of that, and you can here you can make sure that this xn will be 1 for at least one of them. Okay, so this zn is not 0 sequence, so some xn, some xk is non-zero. Okay, that means mod of xk will be 1. So this infinity, this maximum of this znk will be 1. Okay, is this clear? So I mean I am saying this because see, this xn will be 0 if yn is 0, but yn cannot be 0 for all n, because by definition yn is phi of en, and we are choosing when we are, so initially, so when I am saying for phi belong to C0, I am choosing non-zero. Okay, so to be more precise, because for 0 I mean it's not a point, so for 0 it's trivial. Okay, so it is a non-zero linear functional. So for phi equal to 0 you just have to take y equal to 0, that's it. So we have to consider non-zero thing. So that's why, since phi is non-zero, I mean, if you want, I can write it here. Since, let me write it here. Since phi is not equal to 0, this implies yk is not equal to 0 for some k, and this implies that xk is not 0. Yes, I mean xk is 1, and this implies, so therefore this maximum will be 1. Okay, so this Zn belongs to C0 space, and the infinity norm of Zn is 1. Okay. Now you just notice this thing. This phi of Zn, if you see, this is nothing but phi of summation, what was that, xk e raised to power k equal to 1 to n. Okay, and this is, by linearity you can say that this is summation xk, xk k equal to 1 to n and phi of ek. I mean, just the same thing what I did earlier. So this is summation k equal to 1 to n. This is xk, by definition you see it's mod yk by y. So it is mod yk by yk when yk is non-zero. Okay, and else it is 0. So suppose that it is not 0. I mean, just a second, let me complete it. And you know, by definition this is yk. Okay, so this is equal to, I mean, if yk is non-zero, so let me write here that yk non-zero for such k plus summation plus 0, right? So what I am saying here, that you consider those k from 1 to n for which yk is non-zero. Okay, then you can write this definition, and this is equal to yk, mod yk. Now when yk is 0, then also this, it can be included in the summation, and when yk is non-zero, then it is yk anyway. So this is k equal to 1 to n. Okay, so this is your this phi of Zn. Okay, so you have obtained this expression of phi of Zn. Now you know that this phi is a continuous linear functional. Okay, so if I can, so let me say this thing. So this phi is a continuous linear functional on C0, right? So you can say that mod of phi y or phi of x is equal to, less than equal to, c times norm of x infinity. In fact, this c will be the operator norm, so you can write here operator norm as well, that phi operator norm and x infinity. Okay, this is by property, I mean, just by, since it is a continuous linear function. Now so this is true for all x belonging to C0. Now we know that this Zn belong to C0, so this implies mod phi of Zn is less than equal to norm phi and norm Zn infinity. Now you know that this is 1, right, for each n. This is for all n belonging to n. Phi of Zn, you have calculated that phi of Zn is summation mod yn, and modulus, so this is a positive quantity, so modulus of that will be still the same thing. So this is mod of yk, k is equal to 1 to n, and this is less than equal to operator norm of phi, right? This is true for all n belonging to n. Now you see that for each n this is true, so therefore the limit, if you take, right, so it will be from k equal to 1 to n mod yk. Since the right hand side is not depending on n, you can say that this is less than equal to phi, right? Sorry, infinity you take, right? So what does this prove? And you know that this is finite, I mean, since phi is a continuous linear functional, so operator norm is finite. So this proves that the sequence yk belong to L1, and this is done. So this is what we wanted to prove, right? Okay, so far we have proved that So this proves that the T is surjective map. So this proves T, I mean this map, so y going to phi of y is surjective. Okay. Okay, now what we, the another thing was that we have to prove that it is isometrically, I mean isomorphic to this L1 space, right? So notice this. So you notice from here, I think I named here something. So from claim 1 you know, so let me copy this, okay? So you know this one. So this is from star 1. So this is for y belonging to L1. You know this. The another thing is, you notice from here, star 2. So from star 2 or star prime, from star prime you know that y L1 norm is less than equal to, I mean phi. So this is phi y only, I mean just a second. So what I have proved here, so here I have proved that this phi is equal to phi y. So this phi is equal to phi y. So this phi norm I can write phi y now, right? This phi, since phi is equal to phi y. Okay. So from star prime I have proved that this is true, right? In all together this whole thing implies that phi y is equal to y norm, L1 norm, right? So this proves that it is isometric. The isomorphism is isometric. Okay, so this proves the result. Okay, so this was the last step which proves that it is isometric. Okay, is this clear? Is this fine, or do you have any doubt? Okay, so if there is no doubt, let's stop the session here.